We are slowly approaching the end of our chapter sequences and series, and in this section let's now look at the limits of infinite sums. We have looked at infinite sums just now during the mathematical induction. And we will start immediately with a mathematical proof that God exists. It was provided by Friar Guido Grandi in the early 18th century. While you probably may think what absurd idea this is, let me make you aware that there is a so-called ontological argument for the existence of God, which was introduced by Anselm of Canterbury in the 11th century and which is debated until today, so a very famous proof. So here you can read this famous proof of Anselm of Canterbury and, well, decide yourself how convincing it is or not. Stop the film now until you have finished reading and then continue again. So how does this mathematical proof of the existence of God work? Well, Guido Grandi looked at the infinite sum 1 minus 1 plus 1 minus 1 and so on and called it S. Then using method 1 by taking here brackets around the 1 minus 1, again 1 minus 1 and so on, we get 0 plus 0 plus 0 and so on. So S is 0, obviously. However, there is another possibility by putting together the minus 1 and the plus 1 here, so getting 0. Taking again minus 1 plus 1 together, we get 0 again, and we can continue like this. We get always 0 here. So what we get is actually 1 plus 0 plus 0 and so on. So we get 1. And now comes the conclusion drawn by this friar Guido Grandi. Well, man cannot make something out of nothing. However, mathematics can do so, as we have seen, because we made out of S being 0, suddenly S being 1. Hence, there is something that can make something out of nothing, and this is God. Well, I leave it up to you how convincing you find this proof of the existence of God, but let us continue now and let us show that we can also prove that S is 1/2 additionally. The idea is that we factor out the minus 1 for this part here. So we get 1 minus, and then this becomes to 1 minus 1 plus 1 minus 1. So that's what we see here. And what we see here in the bracket is actually exactly the original S. So we see S is 1 minus S. Let's rewrite that. S is 1 minus S. We can add S, so we get 2S equals 1. And by dividing by 2, we see S is 1/2, as said before. Well, this is not enough of strangeness. Let's look at another example, even more astonishing, namely at the infinite sum 1 plus 2 plus 4 plus 8 and so on is minus 1. So S here is just this infinite sum. Now we go and we factor out the 2 from the second sum and on. So when we factor out the 2 there, we get 1 plus 2 plus 4 plus 8 here. The 2 becomes here the 1, the 4, the 2, and so on. So when we look at that, we see what we have in the brackets is just S. So we get S is 1 plus 2S. Subtracting 2S, we get minus S is 1. And now multiplying by minus 1, we find S is minus 1 as predicted. Well, the question is what went wrong in our proof? The problem is that S is not a number. The series does not converge. And so we have only proved the following. If the series converged, the infinite sum would be minus 1. However, we know that it does not converge. We just can have a short look at it and it becomes obvious. So it is the if is a condition that will never be fulfilled. So we can also say if the series converge, the moon would be made out of cheese. Is as true as the other statement. One important remark, the method that we used is correct if the sum converges. So let us now apply this method in example 3 for the sum 3 plus 1 plus 1/3 plus 1/9 and so on, and we'll just assume that it converges, which by the way we know, since you should have recognized that it's a geometric series. But for now, we'll just assume we didn't remark that, and we'll try to find S using the upper method. So S can be written as 3 plus, and now I'll factor out 1/3 from the next summons here. So when factoring out 1/3 from 1, I get 3. Then 1/3 from 1/3, I get 1. Factoring out 1/3 from 1/9, I get 1/3, and so on. So we see S is 3 plus 1/3 of S. Let us subtract 1/3 of S. We get 2/3 of S is equal to 3. We multiply by 3/2, and we find out S is 9/2. So let us check this result using the formula for infinite geometric series. S is A1 times 1 divided by 1 minus R. The A1 in our case is obviously 3, and the R is 1/3, which yields 3 times 1 divided by 2/3, which is the same as 3 times 3/2, and we get as final result again 9/2 as expected.